Well, welcome everyone. Exciting night tonight. We have MC Toon with us. We have Greg Holsapple as well with us. We're going to do a flat earth debate. So yeah, the schedule for the evening is going to go like this. Greg is going to start 5-minute intro and just telling you a little bit about himself and where he stands on this issue. And then Mike will have 5 minutes after him. And then we'll get right into it. Greg is going to start by presenting evidence that backs up his claims. And then Mike will have a 5-minute rebuttal. And then both of them will have a 10-minute open discussion between the two of them. And then it's reversed. So Mike will then have 5 minutes to present evidence. Okay, the other party is quiet. And then after that, Greg is going to have 5 minutes to give a rebuttal, and the other party is quiet, and both will have an open 10-minute discussion. I will have a timer for those of you who are on YouTube. It will be up on the top right-hand corner of the screen, just so y'all can see exactly where everybody is when it comes to the time. For Mike and for Greg, I believe the timer would be on the top center of the screen. And at the end of the debate, we're going to open it up as much, depending on how much time we have. We're going to open it up for live Q&A from the live chat. And I'm also going to be posting a poll on YouTube. Okay, this is only going to be available on YouTube. A poll asking you, who do you think won this debate? Okay, so this is going to be about an hour and a half. The debate, the meat of it is going to be about an hour and a half long. And so, yeah, welcome everyone. Awesome. Good to see y'all. Let's start with Greg. So I'm going to pull up just a second here. I'll pull up Greg, and Greg, I'm going to put up a timer that will give you 5 minutes maximum to introduce yourself and to let everybody know who you are and where you stand on this issue. So let me see if I can get this timer going. This will be 5 minutes, and I'll get Greg up here on the screen. So welcome, Greg, and your 5 minutes starts right now.
All right. Thank you and welcome. Yes, I just, I'm a preacher, teacher, travel, go different places. A lot of Hebrew roots, a lot of, just preaching out of the Bible. I try to take it about as literally as you can see, as you can see me, that just going through the scriptures, I found this, some of the people in our fellowship had brought this to me, sent me messages and sent me different things about, the flat earth and everything. And of course, when I first started, I was like, what is this? That's really got nothing to do with the Bible, I don't think. It's got nothing to do with preaching and teaching and all this kind of thing. But then the more I started looking into it, and they started bringing me scriptures and things like this, and I started saying, well, maybe this has something to do, maybe this is something to do. So I started taking a different stance of it doesn't matter. And, the more I looked into things, the more that I just started finding scriptures and more, just more finding out of what it actually says. So with all that, I just started getting deeper and deeper into it, just like, when we look into Yahweh from Lord or from God, or, when we start digging into things, we just start digging into them. So that's what I started doing. Started praying about it, just going over it. And the average person doesn't think it's a salvation issue, or it has much to do with a lot. But I believe it. The more I get into these even debates or everything, I'm just proud to be here. I'm proud to represent my king. That I know people have different views. I know atheists. I seen our last time that the atheist actually said something, but I believe everything we present in our life means something, and sometimes it's a learning lesson for us. He tells us that he puts us before the world, as sheep to the slaughter. So sometimes it's a learning lesson, and sometimes we just have to keep digging and finding out what it says. So I think it means a whole lot to dig into each and every situation and find out the truth of the matter, and to explore that and to share it with the world. If we are truly teachers and preachers, then we're going to have to get into things that we don't particularly always like. We don't particularly want to. It's easy to take the easy route and say, oh, we all agree. But when we find something, just like with Yeshua, the apostles, Noah, I'm sure Noah didn't like the flood aspect and building a boat and have to build an ark and all these things. I'm sure he probably would have just rather had a whole different aspect to life than that. So that's my kind of point of view, and where I stand and where I'm coming to from is just going with the scriptures, going with the truth, and then utilizing everything that we can. I'm on the same boat as everybody else. I think that we want to find the truth. We're seeking the truth, and whatever that truth is, I think we should abide by it and just use it to our best of our knowledge, and also understand that we're always learning. The Bible itself is a lifelong journey, if you will. So with that being said, that we understand that journey, we understand that walk, and even if we could be wrong, even if something is wrong, that we go to the truth of the matter, just like maybe December 25th, or following something we might have done one time, but we're not going to do it anymore because we know that isn't the way that it should be done. So I will just leave it at that. I just want to welcome everybody. Thank you for having me here. And again, I'm just privileged to be here. And shalom. Yahweh bless.
Well, thank you, Greg. It's good to have you here. Welcome. I see someone in the chat asked who I was. Christopher Enoch. Maybe I should have my name up there, but yeah, I'm just hosting tonight. So yeah, so now I'm going to invite Mike to come on and give his introduction. Let me just stop this timer and restart it. So Mike will have 5 minutes as well. Go ahead, Mike.
All right. Well, thank you, Christopher. It's good to be back. This is my third time here.
Wow.
And I don't know. I'm Mike. I write software, specifically email filtering software. I am a Christian, though the shape of the earth I don't consider to be something that's spiritual at all. You just go and see what shape the earth is, and then if somebody has some particular beliefs about it, then we'll find out if they match reality. Then it's right, and if they don't match reality, then they're wrong. So. If somebody has a holy book that says one thing, but it contradicts reality, well, that's not good for that holy book. Or could be maybe just that somebody's interpretation of it is wrong. So that's my take on the religious part of this. I did study electrical engineering and computer science. I'm not a practicing electrical engineer. I've written software all my career, so I've been doing flat earth debunking type stuff now for almost 5 years, and I've been doing weekly debates on my channel, MC Toon, for almost 4 years. And then I have another channel, Conspiracy Tunes, where I do pre-recorded videos. That's all I have for an intro.
All right, Mike, thank you very much. Yeah, so just before we get into the thick of it here, I do have links to Mike's YouTube channels in the description. I also have a link to Greg Holsapple, excuse me, Holsapple's Facebook page and such in the description as well. And also, if there's anyone that wants to know what schedule are we following tonight, I do have that up on ChristopherEnoch.org. I have it detailed as in regards to who speaks when and this kind of thing. So Greg is going to give a 5-minute presentation of evidence, and then after that, Mike will come in and give a 5-minute rebuttal. So once again, I'm just going to start the timer here, or get the timer ready anyway. Pull up Greg on the screen here again, and so Greg, you have 5 minutes to present evidence starting now.
All right, thank you. Well, I would like to submit the compass. I know it's a pretty regular thing that everybody uses, but I think that when we do this, that we should use those regular things that everybody can use and everybody can see and everybody can, take a look at for themselves. Just a regular compass, north, south, east, and west. And with the compass, that we can see which direction we're heading. Now, with these directions, we can obviously see north and south, as my little instructions and my homemade thing over here is, but we can see north and south. But given that we also have the true north and true south, which we have the wobble and the axis of the earth. Now, with all that being said, we still know we can find our way from north and south with the compass. The problem becomes is when we become east and west. Now, if the earth is turning, then we have a problem, because if east and west is on this compass and I'm in the east or the west, then I have perfectly where I'm at, right? So if I'm in the Middle East, in the middle of Pakistan, I know where I'm at. Now, I also can tell where I'm at if I find a landmark, but that landmark is also moving according to this model, right? So on this behind me, if this is moving, then that landmark's moving. The problem becomes when we start doing something other than that movement. Say I'm in a plane, I'm on a boat, I'm dropped off in somewhere and I can't find my way. So now we have the problem of east versus west, just like the lightning, the east from the west, right? So that's separate from each other. But once this starts moving, then it doesn't really become that way. As we have charts, I wish I had a little bit better stuff here, but as our time charts, as it shows, the sun is moving supposedly across this, right? Or we're moving. One way or the other, something has to be moving for all this to work, right? And I know I'm going to get beat up for that. But my whole problem is, again, once this starts moving, it changes everything. From the north coast to the south, the east, the west, everything, even in the axis, as like I said, we'll give that up. But when we go from the Middle East to America, if we're traveling at 1,037 approximately miles per hour, and that's what we're being told, right? That the earth is revolving every 24 hours approximately. But if that's true, at one point, this east has to become around here. It has to, right? It has to become east to the west for that to work. Just like we see the sun, we see the time zones, we see all this happening. So, if that's actually happening that way, then my compass should tell me this. When I'm in the Middle East, it should be moving just as fast as the earth is moving. It should be moving. It has to, because if it doesn't, we're not moving 1,037 miles an hour. This compass is lying to me, because when I go from New York to LA, then my compass is telling me a different story than what I'm doing. Yes, we'll still give it the north to south, but the east to west, something's got to be happening if we're actually turning like we're told we're turning at 1,037 approximately miles per hour. Then my compass has to represent this, and no compass I've ever seen, according to this one or any other ones, actually represent that movement. So again, I would submit to you that the only way that this compass works the way it professionally does in anything you're in, any boat, car, GPS, whatever system that you're in, it has to tell you to navigate to this place, right? And that's just a given. So without that, we have a problem. And that's all I have on that for now. Shalom.
Okay, thank you, Greg. And so now Mike is going to give a 5-minute rebuttal, and I'm just going to start the timer here. Okay, starting now.
All right. Well, thank you for that. I do have a compass as well. Right here, this is a rated to be an international compass because compass inclination is an issue north and south of the equator. This one is a little better one. It's got a different gimbal on the inside, or a pivot point inside. I also have a globe analog here. This is an actual bar magnet inside of this sphere here. So I got a north and a south. And so it sounded to me like you thought that because the Earth is rotating, that somehow the east and west would somehow move around. And I don't quite understand exactly what you're trying to get at, but I can show you a demonstration here. So I can put right here. My markings are swapped actually. So there you can see your live chat there in the reflection. So if I don't know why. I mean, why you think that? You see, I'm rotating the analog of the Earth along with the analog of the magnetic field, and the north south and the east west are not moving, just like we see. I mean, if you take this compass and you just set it on the Earth, it doesn't flop around all over the place. So I don't know why you'd think that is a prediction of the globe Earth, but it also I wondered when you were saying that maybe you thought that the magnetic field of the Earth is independent of Earth's rotation. It's not. The actual the declination of the magnetic field sticks to, generally it varies over time, over many years, but it generally sticks to one position. So like for on the East Coast it's 15 degrees. The East Coast of the United States. On the West Coast, it's like 19 degrees declination. Going through Minnesota, it's 0 degrees declination. So let me show you this, though, just in case that's what you thought. Here again, I'm just going to rotate on its axis there. So so the magnetic field is rotating independent of the compass. But now watch this. This is important. If I actually rotate it this way, you'll see it flips. You see that? I'll go back this way and the needle will flip again. There it is. So, and then finally, this is kind of cool. If I do this, you can see that it matches actually. Like, so a compass, a lot of people, Greg, you didn't seem to get this misunderstood, but a lot of people think a compass points north. It doesn't. It aligns with the north-south magnetic field. So maybe I misunderstood what you were talking about, Greg, but there I gave you a couple real-world demonstrations of a magnetic field and a compass interacting with each other. Thank you.
Okay, so now Mike and Greg will engage in a 10-minute open discussion. I'll set the timer, and you guys can have at it right now.
I guess the thing of it is, what I was trying to make the point, it was, I understand the north and the south, they obviously don't move that much, but just like when the eastern coast, when it comes around, the sun obviously is not up, right? So the sun's got to, either something's got to be moving somewhere for the east or the west, or the sun's rotating around, right? So the sun is either coming this way, or the earth, even if it's rotating that way, then how does that east never become west? If this is rotating either direction, eventually that has to come around according to the revolvation, right? For it to revolve around at 24 hours, this has to be back here. But this, if it's in East, say East Asia, or like I said, Pakistan, wherever, this is revolving around the world. And if that's revolving around, at what point would our compass not, why does it not tell us that?
I have no idea what your misunderstanding is here, Greg. This is, I think basically, let me summarize. You're confused about this, therefore Earth flat? I don't understand what you're trying to get at.
Right.
None of this makes sense.
Okay. Well, if this is revolving, right? I mean, if this is revolving, it has to, we're told this is spinning.
Yes.
So if this is spinning at this point in 24 hours, this same point has to be here. So if we're all the way in the east, then that has to come around, right?
Yeah.
So the Middle East. So in the Middle East, is that the Middle East or is that a part of the West? It can't be.
Oh
If it's
gosh.
revolving at some point, that has to be revolving.
Greg,
Yes
I think
or no?
you need a geography lesson.
I probably do.
I mean, I'm showing you right now on a physical model right here, rotating that east is still east, west is still west. Everything's relative to the surface of the earth. Does that help? Like the position of stuff, the direction of east, the direction of west doesn't change based on where the globe is rotating or where it's moving through three-dimensional space. It's still, when you're in Pakistan, Japan is still to the east and England is still to the west. Whether or not Earth rotates, I don't know why that even is a thing.
Well, I'm just saying, if it's really rotating, then it has to come around. And at what point, when this comes around?
Well, here,
Like-
let's. Here's. Do you see this little part here? This little
Right.
node, right?
Right,
It's rotating. You see it now? It's on the other
right,
side.
right. Just like
Now it's on
that
the other
little
side. Yeah,
that little tape right there.
yeah.
That
So
little tape. That's so east and west switch. There's no
No.
point, no time
No.
that. How can
No.
that be then? Then we're never. So to go to the Middle East, if I fly the other way, then I'm going to have a problem. Correct or not?
no,
Or I'm just going to wait till the Earth to rotate to me, so I can
no.
jump on a plane. I'll just wait.
No,
The Earth rotates to me, and I'll be there.
Conservation of momentum is a thing. Just not understanding conservation of momentum isn't really going to help you.
Right.
Right? If you're on a bus
Mm-hmm.
and it's moving 60 miles an hour down the road and you jump, will you fling to the back of the bus? No,
I'll
you
fall
won't.
out.
You will not. You will stay relative to the bus. You will jump up relative to the floor underneath you and then come down relative to the floor underneath you. That's because you had motion, forward motion, when you left the floor, and you kept that forward motion while you were in the air.
Mhm.
And then when you landed, you kept it even while landing. In fact, you can play catch with somebody across the aisle of a bus. And we don't even need to think about the speed that we're going. Right? You might be going 60 miles an hour, but you can still play catch as if you are not moving because the entire reference frame is moving with you.
Right. Now, what about these restaurants, the 24-hour restaurants or the restaurants that spin? The same concept, right? If I'm sitting at a restaurant in Berlin and it's spinning, again, it doesn't matter how fast, how slow, but I'm moving and I'm watching the city. I'm watching different parts of the city. At some point, I see the eastern part of the city. I see the western part of the city. Right? So I'm watching as things go around me. And the same thing with this is happening here. Again, you're right, whether it's spinning 1,000 to whatever, but still with the rotation of the earth, I am looking at a different direction. I have to be.
So in your restaurant,
Right.
you stand looking out the window. Just stand there. You have a table to your right, a table to your left.
Mhm.
Now you rotate a quarter of the direction around. That table to the right is still to the right. That table to the left is still to the left. Your right and left didn't change, like your east and west doesn't change when you're on a globe rotating.
But that, you're right, that doesn't change inside the restaurant. But when you're looking outside the building, say the wall of Berlin or whatever the parts of the city, you're watching different parts of the city go by because you're rotating.
Yeah, that's
right?
outside your reference frame. So that would be a good example to consider, that the stars move throughout the night. So yeah, like inside the restaurant, what is outside the restaurant appears to move relative to you. On the earth, when we are look up at the sky at night, the stars appear to move relative to us. The same kind of thing. That's outside our reference frame. Now, is this restaurant at the end of the universe?
No.
Okay. It's expensive to go to the restaurant at the end of the universe, but what you do is you go back in time and you deposit a penny in a bank account that gets just some nominal interest, and by the time you get to the restaurant at the end of the universe, the interest has accrued, so it's a lot of money. Little pro tip there.
Can I take my DeLorean or? Doesn't matter
A
if it goes
DeLorean,
88.
you that would work, or a phone booth, or a police box. Any of those. Yeah.
All right.
All right. I don't seriously, Greg. I don't quite understand your misunderstanding here. The
Right.
magnetic field of the Earth is relative to your position is relatively stationary, but your position when you look out at the stars is relatively not stationary.
All right.
So
I got another little homemade example. It ain't as fancy as your little one there, but this one here, you're right, north and south, but it also moves on its axis, right? Forward, like I said, we ain't going to debate that, but this point is east or west. At this point, when this spins,
that's
I
not.
mean, it has to.
That's not. No,
It's movement. Either
east and west is relative to you.
no. When I'm in, okay, just say I'm in New York, right? I'm in New York, and in 6 hours, this spins. So when that spins, if it's movement, it's got to be movement. I mean, we have to account for that movement. Either it's moving or it isn't. If it's not moving, then of course the Middle East will always be the Middle East. But if it's not,
do you think that when you look at a compass,
mm-hmm.
that when it says east, it's referring to China instead of just the direction relative to you?
No, it's heading east. Whatever east is according to the compass.
East is relative. I mean, there's east relative to your position, and there's the Far East, which is a geographical place. That's not what the compass is informing you about.
Right.
Like if you're in Hawaii and you want to go to the Far East, you wouldn't head east. You'd actually head west. Because the position of the continents are relative to each other, but they're not like you had a point there. You had these toothpicks sticking out the side, like that's
right.
east. And no, that's not. When you look at a compass, that's not pointing to that toothpick position.
Right. So then east would have to change, though. If that's not true east, then true east would change. That's my point.
True east. East is relative to your position.
Okay.
But I see we're about out of time here.
Right.
Okay, so now Mike is going to have 5 minutes of uninterrupted time to present some evidence for his position. So I'll just start the timer here.
All right, I'm gonna. Can I share
What you
a?
think, Logan?
Let's see. Can I share this? Do you see that?
Can
you?
Let me see here.
There you
Okay.
go.
All right. Okay, I'll start the timer. Whoops, wrong timer. 5 minutes.
All right. Well, thank you for that. So, coincidentally, my first topic here is star rotation, and so I I live in the northern hemisphere. When I look north, I see the north celestial pole. When I look south, I don't see the south celestial pole. But when you're south of the equator, you do see the south celestial pole. It's up in the sky. So and that's the center of rotation. So you need to wait, a couple hours, and you can see the actual center of rotation. So this is a time lapse photo from Table Mountain in South Africa. Looking south, this is one from South America. Looking south, there's a center of rotation there. Here is a video showing an actual time lapse. You can see the stars going there. They're going clockwise in the northern hemisphere. They go the other direction. It's almost done here. Now I've not been to the southern hemisphere, so I can't. I couldn't have recorded it. I did record a star trail looking south when I was in Florida, but I don't have that. You don't see the center. So on here, let me show you on a globe. Here's a little diagram of a globe. When you look north on a globe, on the surface of a globe that's rotating, it's predicted that you would see the center of rotation to the north. When you're partway towards the equator, when you look north, you should see that center of rotation being lower in the sky. When you're on the equator, that center one, you should see straight lines coming up and down and then curving both directions. This is, again, the prediction for the globe. When you're farther south of the equator, or just looking south, you should see the south celestial pole, and they should be rotating in the opposite direction. And then when you can look due south on the southern hemisphere, when you're far enough south of the equator, just a little bit, and you don't need to get very far before you see the actual south celestial pole, the center of rotation. Now, this is what the globe predicts. And that means that anywhere south of the equator, when you look due south, you must see the center of rotation. And that's like I showed here, that is what we see. South Africa, we see a center of rotation. South America, we see center of rotation. Same in Australia, New Zealand, elsewhere. On a flat Earth, if there's a dome of some sort over it that's rotating, then you should see in the center, you should see the center of rotation in the center. But when you get farther, when you look south, you should see things moving laterally. There should not be a center of rotation due south that everybody can see south of the equator simultaneously. Obviously, it has to be nighttime for these places, but we see these examples on this bottom there: Bolivia, Cape Town, and Sydney. From sunset to sunrise, the south celestial pole does not change position. It is always due south, always. It does not move laterally. This does not fit with the prediction of a dome of any sort. I don't know how it could possibly work. So this falsifies the idea of flat Earth. And as we see here, it confirms the idea that the Earth is a globe. So there we go. Thus ends my presentation.
Okay, so now Greg is going to have 5 minutes for a rebuttal. So I'll set the timer here. And okay, Greg, you got 5 minutes.
That kind of goes right into the firmament, the windows of heaven and the firmament, and exactly into what you're watching. The firmament itself is what's moving. It's not the earth that's moving. It's the firmament that goes around, and everything that Yahweh created is the way he created it, and these are his timepieces. So when we look at these, we look up, and it says the sun, the moon, the stars. So all these things that we see in Genesis is exactly what we see, exactly like he made them. So we have them, and we use them as, to navigate again and to go into different places. They've used them for ages for going to, ships, to even find the Americas, all the ships, all the different navigators. have used this, which means it cannot be rotating, it cannot be moving, it cannot be a million miles away from them stars, because if we're getting a million miles away per year or however it is, then we could not use these stars to rotate. We couldn't use these things for navigation. It would be incapable to use them for a navigational device. They would be so far behind us, we would pass them up and we wouldn't be able to see them exactly as you see there. So I agree that that firmament is what holds them and what, is what has all them in there, but that is our timepiece. That is how we use not only time, day and night, but it's also how we can literally look up and see what we're, which way we're traveling, which direction we go into, or what we need to, whichever direction that we need to go to. That, and why would that be? Well, it says to go to the feast days, to go to these days and their appointed times. So on these appointed times, we're told that these different stars or Venus or Jupiter or all these, but actually the scripture says these are actually the angels, and you see this in Revelation. So these are actually, the fallen ones are the ones that don't keep track. They don't do what they're supposed to do, hence they fall, and they don't end up doing like they're supposed to do. But the ones that do stay within their positions and do stay in where they are supposed to be, then we can count on them just like he has put them into place. And knowing that Yahweh has made things and he knows the beginning from the ending, then he has put the ones there that we need the most important, say like the North Star. He says, I am the morning, the bright and morning star. So all these things that we see are the Creator's made, the Creator of what he says and what he put there that we can use to, to travel and to do those things with. That's all for now. Shalom.
Okay, so now we're going to have 10 minutes open discussion and start the timer right now.
So Greg, why didn't you address my presentation here? I specifically showed that there is a single point of rotation that is due south from all observers, that's visible for everybody south of the equator. You didn't address that at all. How is that possible? If you say that there is some sort of a dome or firmament, then how could it be rotating around a central point simultaneously in a different point for every single observer south of the equator?
Just the way it was created, that the way that he had made these things, just like the North Star, we have navigational stars. We use those stars and they don't, they don't necessarily move. That there's certain things that as a timepiece that, just like in a clock that's spinning around, we see the numbers, we see the things, but the central part stays the center part, right?
You said, but you said Polaris doesn't move?
No.
Are you certain of that?
I'm not sure.
Maybe you shouldn't have claimed that.
Okay.
Yeah, I'll let you retract it so I don't have to
beat me up. Okay,
Yeah.
well, yeah.
Polaris moves. mctoon.net/Polaris has 500 years of documentation of Polaris's position. All the major stars are charted in the nautical almanacs that are used for navigation, and their positions do indeed shift over time.
All right. Yeah.
So now still, I'm still waiting. How is it that if I'm conjecturing just how what you think based on what other flat earthers have said, that they think that there is some sort of a physical dome over the top and that the stars are embedded in it, and that is what we're seeing when we see the rotation of the sky. But I'm asking you again, how is it that there is a single point of rotation north and a single point of rotation south, and people that are in different areas of the flat earth can see the same point due south, even though their backs are to each other at the same time?
I don't have a good answer to that because I've never really, I've never seen it. All I can say is, like I said, that the way that he made it, and I do agree with the firmament theory that if it's in the firmament of how we see how we see the sun, the moon, and the stars, and see them rotate around.
Okay, so kind of a punt.
Right.
I got it. There is nothing. I know it's a tough question. There's no explanation for flat Earth.
Well, it depends on. You'd have to put it all together, and I just ain't put it all together. I don't want to answer out of place or answer at something that I haven't, no real knowledge of being in this spot and that spot. If I could.
It's okay. No flat earther has put it
right.
together.
Right.
None of them have, but basically the essence of the answer is saying perspective a whole bunch of times.
No.
But it's physically impossible to have a single point of rotation south of the equator and north of the equator, and for people to simultaneously see it when their backs are to each other. Right? You think about that. When you're standing back to back with somebody and you're both looking straight ahead, right? So you're looking in opposite directions. You can't see the same thing. Right in front of you, straight in front of you, you cannot see the same thing. Yet, that's what we see. Obviously, it cannot be flat. There's no explanation.
But
right, well,
right.
we kind of came to
an
an impasse, I suppose.
That.
Yeah.
Like I said, I don't want to speak on something that I have not really a lot of knowledge about and try to be,
Well, then, Greg, will you do this?
Mm-hmm.
Will you look into it?
Yes,
and if
I will.
you find no real answer other than just buzzwords and catchphrases,
right?
Will you seriously reconsider your position?
Oh yes.
All right.
I'm.
That's fair.
Okay.
All right. Well, I'm happy. We can move forward if you want, Chris.
Okay, so we're like halfway through this. Just a little reminder: after this, we're going to have live Q&A from the live chat for a little while, for a few minutes anyway. Also, I'm going to be posting a poll at the end of this, asking you guys, who do you think won the debate? Okay. So, anyways, up next here we have Greg is going to present more evidence. He has 5 minutes to present that evidence. So I'll set it up here and okay, go ahead.
All right. Hopefully we're 1-1, so this should make it 2-1, and by the end of it, we're all going to have a happy night, right? So what I'd like to present to you now is there has been nuclear weapons, 13,080 is what we are told. 13,080 nuclear weapons. Now, when we researched, again, the Earth and the rotation of the Earth, that there's something that's got to be pulling the Earth, and we're told there's something that is pulling this Earth, right? So we're just going to throw all that in there. But with all those nuclear explosions, and a lot of them between Russia and the United States, at some point somewhere, that's going to have to slow this down. It's going to have to possibly put it backwards, right? I mean, if you're talking all this nuclear underground, in the water, all these different things, we have tidal waves, we have all these things that happen over just a little earthquake. A little bitty earthquake causes this, and we feel it across the ocean. But 13,080 nuclear weapons being discharged underground, on top of the ground, all over, and many times, and even some of them, if you look up Operation Dominic, into the dome itself, if you will, that you can see these flashes, you can see these things. You can't really see a whole lot, but you can tell it's going on. So just like the good old merry-go-round, just like something that's spinning, well, something stops that spinning, or something, will stop that spinning. And a nuclear bomb should at the very least, to a spinning Earth that's moving 1,037 miles an hour, again, by that calculation, the effects of nuclear weapons, I have pages and pages, and for times, the blast itself, I mean, we've seen what it does, right? 15% is released as initial radiation, all these things that go on, and all the destruction that they cause, and all these things that they've done overnight in places we haven't seen, the Bikini Islands, I believe, the Toe Islands, all these different places. But we don't even get as much as a time change, right? The sun sets at 6:03 p.m. and it's still setting at 6:03 p.m. There's not a wobble, there's not a wave. All these things have went off, and we ain't got nothing from them, right? So I would submit that all these nuclear weapons had to at least change the time, and we can't find even one thing that's, you know. Now, we also have a study. I'm going to throw this in there. We have a study from those who say the earth will wobble because of, say, New York or so many people in China, that we can get a wobble. And it's a study here that let's try to pull up. I'll just wait. But there's a study that you can look it up, and it's saying that has made the earth change because of human beings, because of people, and being so many in so many different places. So if that is a true statement, if that is a true study, then again, the nuclear detonations should have at least done something to this spinning earth. They should at least slowed it down, again, stopped it, done something, but we never seen that happen. We never seen the sun stand still. We've never seen, a backup. We haven't seen it go in reverse and time spin backwards or any of these things. So it makes me to believe that something's wrong with this model. There's something wrong with, the declination or the spinning or something to do with this, because we can see clearly that these nuclear weapons, and we're told today that there's enough to destroy the planet. There's enough to destroy the whole world. And we may not hear about it, but somebody might be testing something somewhere. We know North Korea and all these things going on. So I would just submit to you that out of all these nuclear weapons, again, was there not a wobble, a stoppage, a slowdown? We have no indication nowhere that even we missed 10 seconds on our clock. The sun, nothing ever did anything. So I see I'm about out of time, so I'll throw it over to you, and thank you for listening. Shalom.
Okay, so now Mike is going to have 5 minutes for a rebuttal, and I'll just start the timer. Go ahead, Mike.
All right. Well, thank you. Hey, Greg, I gotta give you credit here. Not very often do I get a new a new topic. So thanks for that. I do definitely enjoy being exposed to new things. So nuclear explosions, that's amazing. All right. So you said, why didn't it slow down the Earth? And so I'll bring this back up again, right? So if there's an explosion, on this piece of tape here, if the Earth is rotating and an explosion happens while the Earth is rotating, and it's not directed in any one particular direction, like it's not like a rocket engine blowing the other direction away from the rotation of the Earth, then you wouldn't actually expect it to have a significant change to the rotational speed of the Earth. And I don't know, maybe you're talking about also the Earth's movement through space. Same thing. It's not directed, so it's not generally going to have a big impact. The other thing is, now we think that nuclear explosions are big, and of course they are for us. But on the scale of the Earth, they're actually quite small. So the amount of energy released in a nuclear explosion is quite small. Now, you did say that didn't work with the math of the Earth or something like that. You did not show the application of math. I don't know where you probably did that, but maybe you could write it down or bring us through the application of the math showing how it should affect the predicted amount of rotational momentum that it should be changing according to your idea, and how it is that it's directing it in any particular way. But I will say that earthquakes do in fact change the rotation of the earth very slightly. There is an organization, forget the name offhand, but it's an international organization dedicated to measuring the rotation of the earth. They have stations all over the earth with large optical gyroscopes essentially all over the earth, where they're measuring the rotation of the earth. And so earthquakes actually do affect it, but the amount that they affect the rotation of the earth is on the order of many, I don't know the exact scale, but much smaller than a second. It's significantly smaller than a second. And they do actually adjust for it. And your computer, your phone does adjust for it. And I think they do it in June and in December. There's leap years, you know this, but there's also leap seconds and leap much less than seconds, microseconds or nanoseconds, that they do adjust a couple times a year potentially based on the measured changes in the rotation of the earth. So Fukushima is one example of an earthquake that result in an earthquake releases more energy than a nuclear bomb typically. So anyway, so this earthquake that did change the amount. We could look it up. I don't know it offhand, but feel free to have a look at that. So yeah, it's not directed is the main thing. So hey, I'd love to see your math that you went through, because you did make a claim about that. So that's where I'll leave it. Let's have this the two-way here.
Okay, yeah, 10 minutes for the both of you. Restart the timer. Okay.
All right. I am trying to find my little study we was talking about there, but basically, going over that. But I'm really glad that I'm bringing something new to the table, because that's what I want to do. I don't want to bring the same old things that everybody's heard of, because either it works or it doesn't. But with this theory, like I said, that when something explodes, you blow something out of the mailbox, or you put a firecracker on something, a bottle rocket.
Like your style, blowing
right?
up mailboxes.
Right. So when you do these things, though, it has to
Christopher's laughing too. He
yeah,
knows.
he's like, yeah.
He's like, oh yeah.
But,
Yeah.
So going off of that, we have to get at least a wobble. We have to get something that's, we have to get something, and we don't see that. We don't see a whole lot of change. And I know, like you said, some earthquakes and some things happen, but some of these megatons, some of these things that they've put, and just they've exploded even underground or even at sea. Some of these things got some punch to them. So we haven't, as far as I know, I haven't seen any studies or anything that even throws us a little bit off course, or a little bit of the spin slowing down, or anything.
Could you show us your application of the physics of how much you think it should be slowing it down to have a 1 gigaton nuclear bomb exploding underground? How much should it change the rotation of the earth?
Well, like you said, I know it's not going to change
a number.
I think we should at least physically see a something. Maybe it may not stop it, or maybe it may not, but at least a wobble. I mean, maybe we're not going to stop it with this place, and that spot exactly, but we have to see some kind of damage or something being done. Again, like the mailbox, we see it. We don't see the mailbox still intact. We see at least the lid blew off. Something happened.
Yeah. We do see if it's not really deep in the ground. We do see, the ground is quite disturbed. So that's the analog to the mailbox.
Right.
Right. But like if there is let's say you're on a train, and it's a James Bond movie, and the guy shoots a bullet forward on the train, right? So that is now gonna the recoil of the gun is gonna work against the motion of the train.
Right.
How much will that train slow down if that gun shoots? A significant amount or a negligible amount?
Negligible.
Yeah, exactly. So without like actually applying the math, and the other thing is that gun has a direction, and nuclear bomb is goes in all directions. It's without actually like just doing the math and showing the math. I'm like, it's kind of comes up as an empty claim. But I will say this: the A-10 Warthog, the plane, the airplane. Right. It's it's like the plane that the military will never retire because it's so just you can't shoot it down hardly, and it's so powerful. The gun that's in there is a rather large gun. I don't remember the details or anything, but the amount of recoil that gun has is significant compared to the mass of the plane, and it can and it does actually slow down the mass of the plane, the velocity of the plane. I'm sorry, it doesn't slow down the mass. And these things we can calculate. We can look at the mass of the projectile. We can look at the velocity that the projectile has as it leaves the barrel. And that can give us the amount of energy that has been imparted into that projectile. The airplane must, because of conservation of energy, first law of thermodynamics, that there must be a reverse force work on the airplane in the other direction. And so it was in a documentary. I didn't do the math to verify it, but if I remember correctly, they said, well, if you could shoot that gun for not all that long, you could actually stop the plane's forward motion. So that kind of stuff we can do. We can look at the actual math. We can apply it. We can see how much work is done, how much energy is in that, and we can do the math. You didn't do that. So without that, I'd say, well, go find some physicist friend and see if you can do the math for that. It might be interesting to look at. Okay. But I suspect even if we could direct a nuclear bomb in a particular direction, and maybe we could have a series of nuclear bombs and have some sort of a nozzle pointing to stop the rotation of the Earth, how many nuclear bombs would it take to slow down the rotation of the Earth by 1 second per day? There's a number that we could output from that, because there's a certain amount of rotational momentum that the Earth has. We can quantify these things.
Right. Yeah, you're right. I mean, I haven't got all that together. I just finding the new things to present and the new things to bring forward and to see if it's feasible.
Go find a flat Earth physicist.
Oh boy.
Good luck
all right.
with that. I said sarcastically.
I know.
All right. Maybe a flat Earth seismographer, or sorry, seismologist, a flat Earth seismologist, or a flat Earth cartographer, or a flat Earth navigator. I don't know. None of these things exist. Do you know that, Greg?
I don't know.
I don't know.
But you're, we're along the same lines there, I believe. Any net force causing a uniform circular motion, right? Anything that would cause that to even, wobble, stop, move this way or that way is what we need to find out, to do the math and find out.
Well,
as that happened.
I think the Fukushima is a good example because right. I'm quite certain that there was some quantified change in the rotation speed of the Earth. So we could look that up. I don't know how much wobble you might expect from that. I suppose there's some, but it's again, it's the scale. You're missing the scale. It's Earth is really, really large, and in comparison to the mass of the Earth, the largest nuclear bomb ever is tiny. So, and when they say you could destroy the Earth with all the nuclear bombs, I think that's just a figure of speech. You potentially could damage the Earth's atmosphere and ecosystem enough to, destroy the majority of life. But I think that's probably more appropriate than nobody actually thinks that you could cause the Earth to explode like in Star Wars because of nuclear bombs.
All right.
So I'm good.
Okay.
I'm good.
All right. All right. So now Mike will come on and present evidence for 5 minutes. Let me just reset the timer. And starting now.
All right. Well, we spoke of navigation earlier. Well, it so happens that I have this book right here on celestial navigation. I would, without this book, I wouldn't trust my celestial navigation techniques. But I've gone through it and I've done enough I've gotten a fix based on some measurements manually, and so this teaches you how. To go along with this, you need two things. You need a nautical almanac that has the positions of the stars, and it's important to get the position of the stars that are, recent for this current year, because it greatly affects your not greatly, but it does affect your precision. And then you would also need the site reduction tables. The site reduction tables are an application of it's to get your distance and your intersect. So the way celestial navigation actually works is you measure the angle to the star off of the horizon. And then you take an adjustment off of the horizon for the dip and the refraction. They're kind of small, but it increases your accuracy. Knowing that angle, then you take the complement of it. So you take 90 minus that, right? So if it's 45, you subtract from 90, you get 45 again, right? So that's, and then that tells you how far you are from the point underneath the star on the Earth. That's called the geographical position, or the GP. It tells you how far you are from the GP, and that's because on the globe there are 60 nautical miles for every degree. So if you're 45 degrees, let's say you're 10 degrees, the math is easier. If you're 10 degrees, if that's right, so you measure 80, you subtract from 90, you get 10. You know that you are 60 times 10, 600 nautical miles from the GP of that star. And what you can do then is you can draw on a globe, you can draw a circle around that star that's 60 or 600 nautical miles away, right? You have to do this conceptually to begin with. Then you get another star and you do the same thing. It's going to get probably a different angle. Again, you get the GP of it, you draw a circle, and those two circles will intersect in 2 points. So you know you're at one of those two positions. If one of them is on ground and you're on water, well, you know where you're at. With a third star, you can do it again, and you're going to get a single intercept where all three of those intercept. I could show you how that's done visually. It's pretty cool. So I'm going to share my screen here, Christopher. I have a $10,000 sextant challenge. In fact, more than a year ago, I challenged flat earthers to show how celestial navigation works without using the globe, of course, because flat earthers say that celestial navigation works using flat earth. Well, then it should be simple. Just show the process. So the challenge is to give me the process that works. I have measured angles already here, so they don't need to have a sextant. They just need to use these angles here and show the process. And then I will send, if it works, if you get within 25 miles, which is pretty generous, then I will send a second set of star angle measurements similar to this. And the same process needs to get you within 25 miles again. So far, I've had 3 attempts. One by a flat earther that used the globe and also presumed that light works in ways that it doesn't work. I got a second one from a glober who used basically the same model, the same method. And then a third one that used an astrology software that's actually based on the globe. And then he gave up being a flat earther. So when we put these numbers in here, I'm almost done here. Put these in. This models it out right here. I already put them in. This is what it looks like. These are the intercepts. Now that's on a projection of the globe. Here is an actual like globe. So this is where those 3 points intersect. These triangle things, these cone things, are the GPs of the 3 stars. And you can see right there, this intersect is where that reading was taken out there in the Atlantic Ocean. See the United States, Africa, Europe. So given those 3 star angle measurements and the globe, you can find out where you are. But so far, nobody has ever shown it to work with flat Earth. So $10,000 is waiting for the first person.
Okay. All right. So now we have Greg's rebuttal. And I'll just pull Greg up and just a second here. Okay, Greg, go ahead.
All right. Well, looks like I'm get to be $10,000 richer after this, huh? So, I I haven't done a lot of studying on that and a lot of charts and darts and things like that, but I don't see again why that wouldn't work with the same the same things that we see in the sky. I don't see why that would not work with being whether the Earth is flat or round, or I don't see the difference in how they would be. And that's just from the observing again, from looking at what we see, unless there's some kind of different math or different type of something to look at. That it looks like to me that it'd be the same, the same wherever we're at. I understand kind of the concept, I believe, of what you're, the navigation, and like you said, they're going through the navigation. Especially in the water, going on a sailboat, going to Hawaii, or getting to somewhere to use that to know where you are in case you go off course or something, your compass or something goes wrong, that you would need that to know where you're at. But as far as, I don't see the difference of how that would be, the curvature would change how you get your stars or distance, or how that would be different than like I said, just looking up at the firmament and seeing what that would be, or change a different position or anything. But I'm sure Mike's gonna tell me. Thank you. Last part, we got one more, don't we?
And last part here, 10 minutes between the both of you. Or am I right?
Yeah, this is the final this is the 4th round total.
Oh,
Okay,
man.
thought so. Okay.
Yeah.
All right. So I'll set the timer here and okay, go ahead.
All right. Well, yeah, I mean, Greg, you did make some some nuanced claims during our interaction here today that celestial navigation somehow works for flat Earth, but in fact the geometry would be drastically different. On a globe, the stars are very, very far away, far enough away that you can treat them as infinite. They're not exactly, and if you get precise enough you can, but that's essentially how you do it. The stars then are envisioned on a celestial sphere, which is a concentric sphere to the globe Earth at an undefined distance. You don't actually do triangulation. It's often confused. It's called trilateration. There's no triangles involved. You measure the angle. That angle tells you the distance over the surface. If there was a firmament, then there would be a specific elevation to it. And you could actually triangulate the elevation of the firmament. And if there was then an elevation to the firmament, then you would use that knowledge to triangulate your position using flat Earth geometry somehow. But none of that works. People have tried. People have tried, right? The people that have tried to do my challenge have made an attempt, but there is no elevation that works. When I'm in Minnesota and I measure the elevation of a star, assuming flat Earth, and if you're in Israel and you do the same thing, you're going to get a different elevation. Everywhere that you're at, you get a different elevation. Nothing's consistent.
But would that be just because of the elevation of where you're at, or would that be? It's not that much difference, is what you're saying. It's not going to be that much difference between the elevation of, say, where I'm at and where you're at.
Yeah, you could do it on you could do it at the shoreline so that the elevation is essentially the same. But when you're looking at distances of many thousands of miles, an elevation change of half a mile is not a drastic change. Yet the measured elevation with the flat Earth hypothesis is drastically different. So, for example, the sun. I know the sun because it's we don't know offhand where the stars are, but you can, like, in the sky, but we know where the sun is, right? So on the December solstice, I measured the angular elevation of the sun, and I hypothesized that the Earth was flat. And then we know the distance across the ground between where I was and where the sun's GP, because there's 60 nautical miles per degree latitude. It's a fundamental part of navigation. So we know where the Tropic of Capricorn is in relation to Minnesota. So due south of there is a certain distance. You take that certain distance, you take the angle, you can solve a triangle, and that gives us an elevation of the sun of 2,000 miles from Minnesota, presuming the Earth is flat. Well, the same day in Perth, Australia, doing the same technique, you get an elevation of the sun for 4,000 miles. It can't be both 4,000 miles and 2,000 miles simultaneously. And you have the same problem with all the stars.
All right. Let me think here. Okay, so the difference could be, though, because of where you're going across the Earth, right? If you're 2,000 miles apart, wouldn't that be 2,000? Wouldn't that make up the 2,000 miles? And how would you tell? Is the sextant? Is that what tells the? How can you tell the difference or the distance of the stars?
The distance of the star. Well, on the globe, you don't use a sextant to measure the distance to the stars. There's other techniques that probably aren't really relevant to this conversation. But if the Earth were flat, you'd just use triangulation. But you can try it, but it doesn't work.
Right. So when I put all these together and come back, you're going to give me that 10 grand, right? Is that what you're trying to say?
Go ahead. You could be the first. It's been there for a year. This was in response to. This wasn't in a vacuum. This was in response to a group of flat earthers that claimed day after day after day on a live channel on YouTube, claimed that celestial navigation. They really claimed this only works for flat Earth. But none of them ever actually did any celestial navigation. They just said it only works for flat Earth. They didn't do it. And I'm like, okay, do it. Here's $10,000. And none of them did.
So what is it again? What is your claim now? What do you get to?
The challenge.
Okay.
I'll go over the challenge again. The challenge is, and Christopher, when I was sharing the screen, people at home didn't see it. For future reference. The challenge is to present the process for doing celestial navigation using only flat Earth, right? This describes the process of doing celestial navigation using the globe, right? We can find many diagrams. Let me see if I can find one here that show how it works on the surface of a globe. Hold on, I'm gonna get one, but not any flat earthers have ever done it. So, all right. So here's a little picture of the globe there. There's a couple interesting pictures in here. I don't know where they offhand, but that shows how you actually measure that angle. So a sextant measures an angle. That's it. That's its deal.
So you just have to measure the 3 different measures.
So I have the measurements already. It's just show the process, right? Okay. Essentially, it's go over what this teaches for the globe. This is much more complicated than necessary. This tells you how to do it on a moving boat. It tells you how to do it with the sun, with the moon, with different planets, right? You don't need to do that. Just the simple base case. Here's 3 star angles. The observer's not moving, and you don't need to get it within 1 nautical mile. 25 miles is enough. So it's generous for that. So show the process to do it once, send it to me, and then I'll send you 3 new star angle measurements, because if you tuned the process to work just for those 3 stars, well, that's not really doing it, is it? So that's the point, that it needs to work in general, just like celestial navigation really works in general.
Okay. And that's for anybody. Anybody out there can do it.
Open to anybody. Yeah, one of the people that submitted already, but used the globe was a glober, not a flat earther. So
Now, how would you know the difference whether they use the globe or the flat Earth?
because you describe the process.
Okay.
Yeah, that's what the challenge is. Give me the process so that I can do it myself.
Okay.
Right.
All right.
We got Texas Troy in the chat here, trolling along. He's like me and Toon debating where I won. Troy, you goofball. It didn't happen, people. That's fiction. But I love Troy. He's funny. I haven't seen him forever. Man, you better be around more.
So I take it you guys are done for that session?
I think he gave up. I think he just. I think I got him. I think it's at least 1 up or 2.
We'll let the audience decide that.
The mailbox is the winner, right? The mailbox. Hey, and this hard working.
That is. I mean, that looks like a popular virus.
Right. I knew you was going to say that. This is my Australian car. Same on the bottom.
Oh my
So-
gosh.
I made it just for you two.
So, Mike, you said that people didn't see. There was a screen share that you
Yeah,
did.
when I was sharing my screen, people didn't see it.
Which you talking about the sextant
Yeah.
challenge?
So let
Oh,
me.
I don't know.
Yeah, let me. Neither of them apparently did they see. So here, I'm sharing now. So
Okay, I as far as I could see, it was up. So yeah,
all right.
there we go again.
I'm watching the live stream to see if it pops in there. So
Yeah.
all right. Anyway, so I guess let's see. Oh, there it shows up. I see it now. Maybe, I don't know. Maybe it. Do people at home see it? Hopefully you do. So, all right.
And go ahead
All
and
right.
take a couple minutes there since you
Yeah. Well, here's
other
my
people
webpage,
didn't see it. So go ahead.
mctoon.net, and then right at the top, if you just go to home, you'll see here this one here, the Flat Earth Sextant Challenge. You click on that, and you get to this page. It has the official rules are in this file. I cannot change the rules because there's a SHA sum of that. So you go download it. If I change it later, you'll know.
What did you think, Billy?
Here is the original star angle measurements I published March 24th. So we're coming up on a year. There's the 3 stars, Regulus, Arcturus, and Dubby. And then here's the actual, like, the text of the challenge here. And that's what's in the file. But it says, essentially, to summarize, it says, show the process for doing celestial navigation using only flat Earth. You can't use the globe. Anything that you use that where there's some number that you put in there, you need to show where it came from, that it isn't from the globe. So, for example, 60 nautical miles. Well, nautical mile is a portion of the circumference of the globe. That's where a nautical mile came from. That's its actual derivation. So if you use a nautical mile and you don't show where it came from, well, it came from the globe. So that's not showing how flat Earth does celestial navigation. So anyway, this is my second version. There's actually 2 versions. You can do whichever one you want. The first version, you cannot
had
use
more.
the nautical almanac. The second version, go ahead and use the nautical almanac for the globe. So it didn't help. So anyway, and there is the money is in escrow. I don't hold the money. It's in somebody else's hands. And there is the third-party arbitration if you disagree with my answer, and that the escrow holder has been instructed to honor the wishes of the third-party arbitrators. So, yeah, and then Basil says, we're not seeing what you're talking about, only the $10,000 challenge rates. That's all I'm talking about. So, anyway, this was, I don't know, did you see this before? This was the actual results of real celestial navigation, and where those three circles intersect, that's the point on the globe where that observer was. So, all right, I'll stop the share. All right.
Okay, so I'm going to post the poll right now. So we're going to go into a little bit of open live Q&A in the live chat. And so the poll is, who do you guys think won the debate? Now, this poll is only seen on YouTube. I know I am streaming in a few other different locations as well. So if you want to vote for this poll, make sure you're on YouTube. And yeah, so there you go. It's posted. What do you think? And so those of you who are in the live chat, if you have a question specifically for Greg, just put like @Greg in the live chat. If you have a question specifically for Mike, just put @Mike or @MC and we'll take it as it comes. Greg or Mike, have you seen any comments that you would like to respond to in the meantime?
I see somebody called the Great Deceiver in the chat. Is he seems like he's a flat earther.
I don't see any. Maybe it's just my computer.
The Great Deception.
Yeah, so Greg, this is on the YouTube live stream, so you'd have to go to the live stream to see these.
Okay.
Texas Troy's counting for demanding a recount.
I think it's the mailbox. The mailbox is going to put me over the top.
Oh yeah, the mailbox.
I think we was right there. We was right there, and, you know, and you brought out your compass, but I think it's the, you know.
So my friends, when he was in high school, they lived on a country road kind of, and their mailbox kept getting smashed by people playing mailbox baseball. Which, if you don't know, mailbox baseball is where you sit in the back of a pickup truck with the baseball bat, and as you go down the road at 50 miles an hour, you hit mailboxes. And so they got tired of that. So my friend's dad solved the problem. He bought two mailboxes, a big one and a small one, and he put the small one inside the big one and filled the space between them with concrete. Nobody hit their mailbox anymore. That solved the problem. Can you imagine 50 miles an hour hitting a concrete mailbox with a bat?
So we got Calamentos here, says that Calamentos would like to see you go live with the Great Deception.
Me? I would, absolutely. The Great Deception. Bring it on. You can email me, mctoon@mctoon.net, if you want to come on my channel. I do debates every Tuesday. Or if you want to have it here, I suppose Christopher would be happy to host.
Sure thing. Either way. And once again, for those of you who are listening and you're not subscribed to MC Toon, go over there and subscribe. The links are in the description, and Greg's contact information is also in the description as well. So make sure you do that. So we have a question here from Mute Donkey for Greg. Where is the East and West Pole?
The east is totally in the far east, and the four corners of the earth, just like the scripture says, right? He said he called them all from the four corners of the earth. So the four corners, you have the total east, just like the scripture says. Total, it's the east is far from the west.
Is it a circle or a rectangle?
No, I actually think it's a
parallelogram.
four-cornered, pillared type thing. That's what I believe. But
one of my favorite bands is Pillar.
Right?
Go look them up. Pillar, great band. Yes, Quinlan is asking, isn't smashing mailboxes a federal offense? It probably is. You got some other questions there, Christopher?
Just looking through some here.
Next Pro says, explain to Greg, to me, says, explain to Greg he can learn the reality of our wonderful universe. It's far larger and more splendid than any snow globe. There we go. Yeah, the East Pole and West Pole, Greg, there is none. That's so silly.
Hey, I'm good. I'm good.
Texas Troy says, I do know good metal, and that's all he will give me. I sent you a whole bunch of my favorite bands, didn't I, Texas Troy? If you like metal, there's a band called Tourniquet. So good. Microscopic View of a Telescopic Realm is my favorite album from them.
Here's a question for Greg. What evidence would you need to reconsider your position on flat Earth?
What evidence would I need? Well, I'm just, I don't know, that's a pretty, I mean, a lot, just proving the, because my stance, like I said, coming from a preacher, coming from the Bible, and I know a lot of people say, well, that's up to interpretation and different things like that, but when you're talking about the windows of heaven, the pillars of the earth, the different movements, it says that the earth is still and stationary, the sun stood still, even the sundial, the things that we see, I would have to see this, just like the things that we went over tonight, that I will go into these things, and I love to study. I mean, that's where where I'm currently out, because of not just myself, but studying a thing out. So if it, the physical evidence as well as matching up, I'm not going to be blind and act like I don't see things. I think some people, they follow something because it's the new trend. The flat earth is the new trend, and let's go and make. But, as far as me, me and my house will serve Yahweh, and that means truth, no matter, even if you have to come back and say, look, I studied this out and give me my 10 grand, or, gee, that was humble pie and I kind of got it wrong. So, just the evidence of finding a thing out for myself and finding it out and seeing, if that, just like you said, if we can put these things together and see that's pure truth, and that would be, the evidence for me, if that makes,
I see that 11th Champ is a fan of Tourniquet, or at least knows of Tourniquet.
We got Basil asking, how can air pressure atmosphere exist next to the vacuum of space, and also something about nuclear bombs?
I think he's trying to channel his inner Flurf, because that's a common question from them. So, how can air exist next to a vacuum, air pressures? Well, the answer is that it is positive pressure everywhere. So there is no perfect vacuum. A vacuum in relation to the surface of the Earth to space is a difference in pressure. And there is a pressure differential. In fact, if you install the barometer app on your phone, you can, between this elevation and this elevation, you can measure a difference in pressure between these two. So from here to here is a vacuum. There's a vacuum right here compared to here. It's a small vacuum because it's the differential. So you can see in high altitude balloons that people have released, including flat earther Dwayne Kellum, where he has a barometer on the actual balloon and he has the air pressure shown on screen, where from ground level to 120,000 feet, air pressure went from whatever it was at ground level to less than 1% of ground level pressure at high elevation. Well, if you went from that to, that difference in 120,000 feet, and there's only 1% left of the original pressure, well, to get the rest of the way to 100 kilometers up or 1,000 kilometers up, you don't need a whole lot of difference in pressure anymore. You've already removed most of it in that difference. Also, nuclear bombs.
That's right. Nuclear bombs, they do it. But to go from, like you were saying, to go from the pressure we have into the vacuum of space, right? If that's what he was asking, maybe what I got out of it anyway. If he went into the vacuum of space, at what point do we go from that point of the vacuum is there? So if I'm an astronaut in my spacesuit, at what point do I have to wear my spacesuit? What point did I have to worry about having a rip in my body becoming imploding? At what point is that
exploding? Yeah.
Well, if you was in vacuum, would you not implode?
You would not.
You sure?
Yeah.
All right.
You'd go the other direction. So yeah, at what there's a certain pressure. Each of those has an answer that is a certain pressure.
Right.
So I don't know offhand what pressure a human body can sustain, but if you're in an airplane at 35,000 feet and you depressurize the plane, there isn't enough air pressure to stay conscious for very long. So somewhere high, but you won't if you put those little funny masks on, right? You will make it at some higher elevation or some lower pressure. You would start to feel an issue with the pressure, and you'd potentially get the bends, right? As nitrogen exits it, the liquid state goes to its gaseous state inside your body. That's a problem. Essentially, they say your blood boils at some low pressure.
So Kevin asks, Greg, how high is the firmament, and is it possible to bounce radar or laser off of it to measure it?
That's a very good question. The firmament, I believe, is where we see the stars, and where, I think a lot of people have the same concept there, that the firmament is, I don't know the measurement, I don't know how high it is exactly, but I would say that, the Tower of Babel kind of proves they was doing something, and that's why it got destroyed and they got kicked away from that.
How high do you think that was?
I'd studied that before, and I know they was getting kind of up there, but the whole thing about that, then you're talking about your pressure and your vacuum and all that all comes into play too. So
do you think it was higher than the Burj Khalifa?
See, I think they got pretty high, because it said they had one mind, one accord. So I think they was doing a pretty good job, which goes into the skyscrapers, all these different things of how high can man get before they're stopped. So, but if we use the right measurements, I do believe if you had like a laser, the right measurements, the right tools, the right ways, then I believe we could measure the stars. I believe it's all, to a point, but we also have to go back to the verses that say that this is unmeasurable, that we are, on something that Yahweh put together. And that's another thing, I think, between the globe, because we know the measurements of the globe, right? It's the circumference, we know all these things.
Do, yeah.
So now we're coming again to another point of, was that changed or is that true? So that's, these are all the questions of, again, trying to find that. But I do believe we can see what we see. You see some stars, they look a little farther away than the others. So if you had the right equipment, I believe we can find out, the distance of that.
Triangulation if the Earth were flat, you could just triangulate the elevation of the stars, but it doesn't work, which falsifies flat Earth. Also, the fact that the sun sets falsifies flat Earth. The sun, if the Earth were flat, due to perspective, the sun should never be anywhere near the horizon. You should see it all the time, and its angular size must change dramatically throughout the day. I've personally measured the angular size of the sun using a solar filter on a P1000 camera, the flat earther camera of choice, and it did not change dramatically.
Question: do you feel that the want of being in a flirt club or flirt social group brings out the liar and or shilling people?
Go, Greg.
What was that again?
Do you feel that the want of being in a flirt club or flirt social group brings out the liar or shill in people? It's a question.
Oh, what is the fluff?
Flurf.
Oh, what is that?
A flat earther.
Oh, okay. I do. I actually believe, people are people, and given any new thing, they're going to follow a new thing. I think, the things in movies, the things in Men in Black, that, I think they're going to follow them. But I also think that when you open your eyes and you see back in history and you see that people, what they had and what they used is what we still use today in some aspects. So, but I do agree that, people are followers, and they do kind of parrot what they hear. They do kind of, they're going to say what they're going to say. They're going to follow something just because it's new, not because it's a truth, or not because they're trying to find the truth of the matter. That they're going to, just going to jump up board and do something.
If I could answer that, I think it is sad though, because the Earth is not flat; it's factually a globe. So that people who then fall for the trap of the lies that is flat Earth, then they start repeating these things that are not true, which are lies, which makes them in some definitions then a liar. So yeah, it does in that aspect make somebody into a liar. For the Tourniquet fans in there, one of my favorite songs by them, silly childhood game Uncle Wiggly. I cower in abject horror approaching space number 109, home of the gaunt and haggard shell of the Skeezix. Go listen to that. Good song. Sadly, Ted Kirkpatrick, the drummer who was the main guy behind Tourniquet, died this September. Very sad to hear that recently. And Shane Lane is saying, answer my 3 recent questions.
Oh, Shane Lane.
Yeah. Do you know Shane Lane?
Yes, he's one of my friends from the... Yeah.
So Shane says, everyone knows the higher we go, the farther we see. If the Earth was flat, this would not be the case, as you would be able to see all the way to the end of the planet from any place, without relief, even the sea. Well, a powerful telescope, you would see from New York to Madrid, but that's not possible due to the curvature of the surface of the Earth. This has been shown since ancient times, and that is why lighthouses are placed on top of a tower, so they are visible from a greater distance, and vice versa. If you are in port and you watch get caught up to them. So yeah, if there's nothing in the way, there's no reason why you would not be able to see anything. Things like, the point of, well, from the ground you wouldn't be able to see the Burj Khalifa or Mount Everest because there is the thickness of the atmosphere in the way. True, but from the top of Mount McKinley or you should be able to see Mount Everest because the atmosphere is so thin. Or from an airplane you should be able to see the Burj Khalifa or Mount Everest anywhere. But we don't. We just see this crisp edge to the horizon.
But on the, just like you said, we do have a point of known, that we can't see. Just like if you're in the woods or even on the railroad track, there comes a point, that can be as straight as can be, as flat as can be, but there's a point where you don't see the train anymore. There's a point where you can't see the track. It all just kind of comes up to view. So,
well,
eventually,
if it gets too small to see, sure.
Right.
But if with the correct optics, you should be able to see it. Yet that's not the case. There can be things just 10 miles away, but if they're low on the horizon, if they're low elevation across water, you can't see them because the curve of the water blocks them. You get higher and you can see them. So on flat Earth, you're actually getting farther away from something if you just go straight up because the hypotenuse of that triangle. Yet somehow you see it now when you couldn't see it before. In the horizon, the crisp edge of the horizon cuts it off. That doesn't make any sense.
Mute Donkey asks a question for Mike. What is your quest?
I seek the Holy Grail. But he has 3 questions. You answer. You ask the second one.
No, I got a good one. To Mike and Christopher, that if somebody beat this challenge, somebody took your challenge, somebody did it, or somebody showed you without a doubt the same thing, that the earth was indeed stationary, or they could prove it, would you change, or would you say, no, that's your made up story?
Sure. I think the Celestial Navigation Challenge is a great one.
Mm-hmm.
And we got just 10 days from now will be a year. And we all know there's a good number of flat earthers on YouTube that are this is all they do, right? They're not employed, so they'd be all over it if to get that $10,000. But no.
So you've had this out almost a year, you're saying?
Yep, and it's March 24th was the initial. 2022 was the first when I first published it, and I did a video on it, and then I updated it to allow to be a more broad one, so that both challenges still active, to allow using the actual celestial or nautical almanac. I was very generous, right? I didn't require them to chart their own stars and put it into their own celestial or nautical almanac. They can use it. I mean, it's funny because the nautical almanac positions the stars in a celestial sphere. So I mean, it's kind of a lose. If you do use the nautical almanac, you've just admitted that the Earth is a sphere. But they still haven't done it. Texas Troy is wondering, Megadeth or Metallica? Megadeth.
So how could you use it? What you're saying, though, it's almost like a trick question, right? So if you use the globe to get it, then you, by default, lose. So how could you use the flat Earth with that navigational? You'd have to come up with a different...
Of course. Yeah. All celestial navigation is based on the globe. All of it. You read here, it's just the entire process is built in. So if somebody says celestial navigation works for flat Earth, then they would need to show the process. This isn't the one that you get to use, though, because this shows how it works on a globe. Any position on the globe can be determined using celestial navigation and the knowledge and the process in this book. So I have just a little bit of time left here before I gotta go.
So if you...
Go ahead.
So if you went back to the Mayflower, or you went back to some of the other naval, and you used their navigational system, would you accept that?
The process is I have 3 star angle measurements.
Right.
Whatever system you use, as long as it's not based on the globe, you got it. Yeah. And you don't, and I'm clear, you don't have to use latitude, longitude. You can give some other way to identify the location. Latitude, longitude obviously works pretty well. It's embedded in everybody's phone.
So far, the poll has 66 votes, and 63 of those 66 votes for Mike.
Man, I knew it. But see, he's got a following. I mean, he's bringing his crowd with him. I got
Here's the question: Who voted for Greg? Greg, did you vote?
No, I didn't.
I didn't vote either. I said dismissed.
You didn't vote for me, Mike?
No, I did not. I can't even see the poll anymore. I dismissed it.
I didn't vote myself, so
There it
I
is.
thought for sure, Christopher, you'd have wrote it. A fellow brother did not vote for. I just
I didn't vote
see,
for either of you.
see, oh.
I didn't cast my vote either way. All right,
See,
so
all right, all right.
well, you
Well,
know,
I
there's
appreciate. What'd you say? 3 votes? 3 votes. I
There you go.
appreciate
You
you.
got 3. I'm guessing Texas Troy's one of them.
That's better. That's better than 0, I guess. You know?
another one just came in for Mike.
There we go. Thanks, Mike.
I got pass Queen B, Pa Queen B. Probably voted for you too.
There's one right there.
All right.
Okay.
Well, I should get going here pretty
Yeah.
soon.
Yeah. So we'll wrap it up with that, and just want to thank you, Mike. Really appreciate it. It's been a blast, and you as well, Greg. I really appreciate it. One last time, everybody that's listening, please go to the description and make sure you sign up or follow, subscribe to Mike and Greg as well. All right. So yeah, awesome. Okay, we'll wrap it up as that. Thank you very much.
Yeah, thank you. It's been good. Thanks, Greg.
All
Thank
right.
you. Thank you. Have a good night.
Thank you.
All right.
Night.
Bye-bye. Okay. Okay, well, I'll wrap it up as that. So thank you everyone that's watching. Again, please go and make sure you follow and subscribe to Mike and also to for Greg as well. We'll be back tomorrow evening at 7 p.m. Eastern. And right now we're going through the one of Josephus's books, the ancient historian Josephus. So we're reading through that. I am saving the flat Earth topic for just specific days, certain days. So if those of you who are listening, if you're interested in coming back on and expressing your views or evidence or whatever when it comes to flat Earth, I please ask that you would respect that you do it in context, in topics. So I have been addressing the flat Earth topic on a semi-regular, well, pretty much a regular basis now. So anyways, thank you all for listening. Thank you for your questions and your comments in the live chat. Appreciate that. Before you go, make sure you leave a like if you like this, and subscribe as well if you're interested in this kind of stuff. All right. Thanks again, everyone. And we'll be back tomorrow evening. We do this every single evening at 7 p.m. Eastern, except for Saturday, and that's at 2 p.m. Eastern. So thanks again, everyone. Love you guys. And as always, I pray for every single one of you that the Lord bless you and keep you, make his face to shine upon you, lift up his countenance upon you, and give you wonderful, wonderful shalom. See you tomorrow.